Previously learned about giant ionic crystal lattices. We've learned that they form from ions which are oppositely charged, which are held together by a strong electrostatic force of attraction, and they're held together in these crystal structures, this network of oppositely charged ions, and they generally tend to form these solid crystal structures. In today's video, we are going to look at the properties of these crystal structures. Before we do that, we're going to take you back to some very basic chemistry you learned at junior cert. This is very simple stuff, but it's relevant here. So let's say here, this here is a container. And in our container, we have a solid substance. So to make sure everyone understands it's a solid, I'm going to draw it like this. The particles are arranged in rows of 3, where all the particles are touching each other. There's no spaces really in between the particles. They're held tightly together, and they're arranged in these regular rows of 3. So this here represents for us a solid. And we know that you can take that solid and you could turn it into a liquid. Okay, you could take it, turn it into a liquid by doing something called melting. We could melt it and turn it into a liquid. Okay, so when it turns into a liquid, then we have to draw the particles rearranged because they're not in that same structure anymore. Instead, they have been given a little bit more freedom to rearrange themselves in a slightly different pattern. Okay. Now, what we could do is we could take a thermometer and we could add it to the solid to find out the temperature at which it started to melt, the temperature at which it went from being in a solid structure to over here being in a liquid structure. And we would call the temperature that this happens at, we would call this the melting point. So the melting point is simply a temperature at which melting happens, or any change of state. If it was a change from a liquid to a gas, then it would be a boiling point. So the point bit, this bit here, just refers to some temperature. So melting point. Now, obviously, not every solid and liquid is going to have the exact same melting point. Of course, what we're doing to get the solid to melt is that we're adding heat. We need to add heat to the solid to get it to melt. And what the heat is doing is that it's trying to weaken the forces of attraction between the particles. So we know that there are forces of attraction holding these particles together, and the heat or the energy is working to make them weaker. And once they become weak enough that now the particles have a little bit more freedom to slip and slide past each other, then they start to behave like a liquid. So instead of being stuck together in these rows of 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, they're a little bit freer to kind of slip and slide, drop to the bottom of the container, spread out, and now behave like a liquid. Okay, so now that was a really important piece of revision. So the melting point of different substances can be higher or lower. So example of a low melting point might be 0 degrees Celsius. Example of a high melting point, some things don't melt until 1,500 and even more degrees Celsius. So different things, different substances have different melting points. So what does it depend on? Well, the thing it depends on is how strong are the forces of attraction between the particles. If a substance has very strong forces of attraction between the particles, then this takes a lot of heat, a lot of energy to weaken them enough that it can become a liquid. Now, it so happens that the type of force of attraction in ionic substances is they have this force called the electrostatic force of attraction. Electrostatic force of attraction. And this is a very strong force of attraction, very strong. And what this means is for ionic substances with this electrostatic force of attraction, it takes a lot of energy to turn them from solids to liquids. And it also takes a lot of energy to change them from liquids to gases. So a property of ionic substances is that they tend to have high melting points and high boiling points. High melting points and high boiling points. And again, why is that? Well, it's because the electrostatic force of attraction between particles is strong. Okay. All right. So what we're going to do is we're going to flick over here and we're just going to read a little bit here. So this here is what we need to know, that ionic substances have high melting points and high boiling points. So definitely make a note of that somewhere in your dictionary. Pause the video, do that now. All right, let's look at the explanation. I have explained it already, but we're just going to recap it. In order to melt or to boil an ionic compound, you first need to break some very strong ionic bonds, so very strong electrostatic forces of attraction. This requires a lot of energy, more energy than in other substances, and therefore ionic compounds have high melting and high boiling points. This means that at room temperature, which is a relatively low temperature, about 20 degrees, so not a high temperature, these are usually hard and brittle solids. Okay, so they're hard structures and they're usually like crystal. You know what crystals, like salt, for example, is a crystal. Brittle just means easily crushed or easily broken. If you crush them, they'll break into little pieces. That's what brittle means. Okay, so they're usually hard, brittle solids. Right, that's one of the properties. So we call this property 1 of ionic substances. Property 1. Okay, that's the explanation, and that's why. Again, looking at this diagram, the one last time, here is an ionic crystal lattice of sodium bromide, crystal 1 to 1, so 1 bromine for every 1 sodium ion. And in a solid structure, the ions are fixed in the lattice. They cannot move. They are stuck in place. But if we provide enough heat, we can turn them into a gas. So into a liquid and then to a gas if we keep applying enough heat. And in gas, these ions are free to move. So they're able to spread around now. They're moving freely. They're not stuck together anymore. So this is what happens when we turn into a gas. Same is true for liquids, but it's easier to visualize if we look at a gas. So again, these are free to move around the place. They cannot do that when they are solids. High melting, high boiling points. That's a really important property. The second property we're going to look at is about their ability to conduct electricity. Again, a quick crash course in electricity. For electricity, for an electric circuit, what we need is a power supply, something like a battery or a socket to plug in. So we've got a power supply, so a battery or a socket. And for an electric circuit to be made, we need then a conductive wire, so usually a metal wire. And we have to make a complete circuit. So the electricity has to be able to flow all the way around the circuit and back to the power supply. And this is because we have charged particles, usually electrons, flowing in the wire. And for them to flow, they need to be able to get from one side of the power supply around to the other side of the power supply. Okay, so they need to be able to go around like this. If for whatever reason they cannot go around to the other side, they stop moving, they stop flowing. So say, for example, we were to break the circuit somewhere. Say we were to make a break in the circuit just here where I am opening up this circuit. Now, what would happen is that the electricity would stop. Oops, I didn't mean to do that, sorry. Now what would happen is that the electricity would stop to flow. Okay, so it wouldn't go around anymore. So I'm rubbing out the arrows. Now, a way to get this to open up again would be to put some material into this break in the wire, which lets electricity pass through the gap, basically. So we need a material. So say we stick a material in here, which now lets the electrons flow through it. Now the circuit can go and it can flow again. So a material which allows this to happen is what we call a conductor of electricity. This lets the current through. These are things that we might have learned about before, things like metal. Okay, metals are usually good conductors. Whereas if we put a material in and it doesn't let electrons pass through, so sorry, my rubber's really acting up here. Let's say we put a material in here and it doesn't let electricity pass through it. So we're going to put a big X here to show that it doesn't pass through. We don't have a conductor here, we have something called an insulator. Okay, so these materials have to be either things which allow these charged particles to flow through them, then the conductors. If they don't allow charged particles to flow through them, then we call them insulators. Things like wood, glass, most gases like air, for example, are insulators. These don't let. So again, the circuit will not work if it's set up like this with an insulator in it. Okay, so what about ionic substances? Because that's what we're interested in here. Are they conductors or are they insulators? So to test this out, let's say, for example, we put we had a big giant crystal of sodium chloride. Okay, so we had a big giant crystal, solid structure of positive and negative ions connected together, and it was a big giant crystal of sodium chloride. We have positive and negative charges like this. The question is, can it conduct electricity? Is it a conductor or is it an insulator? Conductor or insulator? All right. Well, it has the potential to be a conductor, and I'll tell you why. It has the potential to be a conductor because it's made of charged particles. So the charged particles, in theory, could carry the current across the gap. Okay, so for something to be a conductor, it needs to have two things. It needs to have charged particles, which our crystal lattice does have. Tick, yes, perfect. It does have charged particles. It's got positive and negative ions. But conductors need to have another thing. They need to have their charged particles. They need to be free to move. So they need to be able to pick up energy here and flow and actually move over to here. Unfortunately, in a crystal lattice like this, all of the ions are fixed in place. So this positive ion, for example, cannot move over to here. It's not free to move. It's stuck in place in this rigid, solid structure. So unfortunately, in an ionic crystal, they are not free to move. So they are not conductors when they are like this. Now, there is a way we can get them. There's two ways which we can get them to be able to move. So we know there's charged particles. How can we get them to be able to move? Well, the first thing to think about is, well, what happens if we take our crystal structure like this, positive and negative alternating ions? I'm just going to draw them 6. Here they are solid. What would be to happen if we were to take them and melt them? Well, what would happen is the particles would now separate from each other because they're now turned into a liquid. They're not stuck together as tightly anymore, like this. And now these are the same ions, but they are in the liquid form. They have been melted. These are now free to move. Okay. Whereas over here, these here were fixed in position. So these ones here in a solid cannot move, but in a liquid, they can move. So in this case, we have now ticked both of the boxes. Okay, so we now have charged particles free to move when the substance is melted, or we say when it is molten. When an ionic substance is molten, it can conduct electricity. It is a conductor. When it is solid, it is an insulator. So solid ionic substances are insulators. Liquid ionic substances are conductors. There's another way we can do this. We could take our solid and we could add it to water. When we add our solid ionic substance to water, what happens is that the substance dissolves. And dissolving, what happens in dissolving, just to keep it really simple, is that the water molecules that are in here, in the water, are able to pull apart the ions. So it's kind of similar to the process of melting, but it's not the same. Okay, it's definitely not the same. We don't want to say a solid melts when we put it in water. It dissolves. But what dissolving is the water molecules start to pull apart the ions. So essentially, again, you've created the same thing here. You've created free ions that are free to move around in the solution. This here is what we would call an aqueous solution. Aqueous solution of your ionic substance. Aqueous solution of sodium chloride, potassium chloride, something like that. This is also a conductor. Okay, so now we have made conductors from something which originally wasn't a conductor in two ways: by melting and by dissolving. Okay, so that's another thing to take down. Property two is that ionic substances conduct electricity in two scenarios: when molten or dissolved. They're the two conditions in which this can happen. They won't just conduct them when they're plain solid form. So that's property 2. So property 1 again was that ionic substances have high melting and boiling points. Property 2 is ionic substances conduct electricity when they are molten or dissolved, only then. Okay, so it's really important. All right, let's go back and just very quickly take up. So second property, so this is property 2, is that ionic substances conduct electricity when molten, when liquid, or in a solution. All right, so in order for a material to conduct electricity, there need to be charged particles and they need to be free to move. Two conditions: charged particles, free to move. Ionic compounds are made of charged particles, so tick, they do have charged particles, but they are not free to move because the strong bonds holding the lattice together. So that's that. Here's the lattice, strong bonds holding together, not free to move. If you melt the substance, then the ions become free to move and carry charge. If you dissolve them in water, then the ions are also free to move and carry charge. So here's that process. Here's our ionic lattice, for example. Here is our liquid water. Both of them by themselves are conductors. So we don't have charged particles free to move. So ionic lattice and liquid water. There's no charged particles in the liquid water. There is in the ionic lattice, but the particles aren't free to move. Put them together into a solution down here. So that's what we have here, an aqueous solution. And now you do have charged particles, the white and the green ones, that are free to move like this. So I'm drawing arrows to show that they can head around wherever they want. So if you put an electric current in there, these can carry the current from one side of a wire to the other side and through the gap that we drew earlier. Remember up here. So if we go back to our wire, sorry, where have I drawn this? Oh yes, here. If we go back to our wire and we were to rub this out here, if we were to put in here our aqueous solution into this gap, okay, if we were to put in here our aqueous solution into this gap, just here, then it would be able to conduct electricity across. All right, guys, I think you guys are ready to answer some questions. Now I'm just going to rub out this stuff because I don't want to give you too much help for, I don't want to give you too much help with the answers. I've explained it to you already, so I'm just rubbing this out. All right, what I want you guys to do is, first of all, what I want you to do is I want you to pause the video. We're going to do 101. I want you to pause the video. Sorry, where are we? Yeah, pause the video. I want you to copy down these 3 diagrams and then use these labels to label these diagrams on the right. So copy these 3 things and then add these labels here. Pause the video and do that question now. Okay, so let's have a look at what you should have done. Well, first of all, easy one, I'm starting off with water. So this here is the water. Hopefully that's what you labeled. It's a liquid. Free ions. Where do I see free ions? Well, these are not free ions. They are ions, but they're not free. So these things down here, once they're dissolved, these are free ions. Solution. This is the solution. Electrical conductor. This one here is the only electrical conductor here. Electrical conductor. This mixture up down here. What else have we got? Giant ionic lattice. That's here. Giant lattice. What have we got? Electrical insulator, that's also here. Electrical insulator. And actually, both of these things are electrical insulators, not just one of them, both of them. So that's that one gone. Sodium ions. Well, that's probably here, Na plus ions. But I also have Na plus ions in the green ones up here. So these are both ions, it's just in the bottom one, they're free to move. All right, I think that's all of the labels covered. So well done if you did that. What we want you to do now is complete the questions 105 to 109, and you should be able to manage all of them, I think, now. And I'll see you the next day in class.